the last class we had seen how speckles are formed. We had also looked at what is objective speckles and what are subjective speckles. And I said in subjective speckle you use a lens. In the case of objective speckles you do not use a lens, and you normally perceive only subjective speckles, because human eyes have a lens. So, when an object is illuminated by laser, what you perceive is through a lens. So, it is always subjective. You need to take special efforts to record objective speckle. Now, what we will do is we will go and see what are the speckle methods that we can think of and what are its key features different from hologram interferometry. So, the first thing is, unlike hologram interferometry, which requires a very high resolution recording medium, the speckle fringes can be easily recorded by a CCD camera. It is lot more simpler, but here also you need a good camera for you to do it. And what is done is, by selecting the appropriate aperture size, the speckle size is easily adjusted to the size of the pixel of the recording camera for high contrast fringe recording. So, you have a provision by which you can adjust the optical system until you get good fringes in your recording medium. You have a provision to do that. And if you look at speckle interferometry, it is again same as hologram interferometry. It is very similar to what is there in hologram interferometry, and we had seen that hologram recording is a lensless photography. Once you come to speckles, we record only subjective speckles, and subjective speckles are recorded by a lens. So, the difference here is the image is recorded using a lens. And the example what I have taken here is from a MEMS application, because we had seen whether it is holography or speckle interferometry, they are ideally suited for small scale object measurements. And what you have here is a pressure sensor, and I can change the load here, and you can see the fringes, and first impression you get is they have very low contrast and they are not as smooth as what you get in photoelasticity. They have specular, you will see dots everywhere, and you have collection of dots. So, you have quite a difficult for you to extract information. So, in all these speckle interferometric methods, people spend lot of effort on filtering. Filtering is a very important step in speckle interferometry. And what you have here is, all these modern techniques, they employ computers. Because of computer processing, the double exposure technique is done digitally. So, initially you stored the initial configuration in a file and use it for viewing the deformed configuration, and it is easy to see fringes in real time as the model is loaded. So, what you find here is you are able to see fringes in real time. That is because of your computer processing of data, and you have fast computers to process image information quickly, and it gives you a semblance of real time appearance of fringes. And when you want to paste a strain gauge, you have to have a elaborate preparation. Same is the case when I go for photoelastic coating application. Compared to these methods, surface preparation is simple. The surface is painted white with a matte finish for speckle formation. You want a specularly reflecting surface. So, you want to have only a simple surface preparation, but even the simple preparation is not simple in the real sense. You need to have some practice on applying your white paint uniformly. It should not have smudges on the surface. When you come to experiments, you need to develop skill. The methodology is discussed in comparison to other techniques. This method is simple, but even a simple technique requires some kind of a skill development, and skill development comes only through practice. You can't do it on one day. One day you wake up and then you want to go and do speckle interferometry. It is not possible. You need to have some training and perfect the steps involved in this. Then you go and make measurement. Your measurements will become reliable. So, simple or difficult is a relative term, but you have to get a uniform thin coating on the surface. And we can also have a look at the close up view of this, and this is actually a microscope which is used, and you have a pressure sensor which is very, very small, and you see the fringe pattern of this, and this was done in Professor Kotial's lab, Applied Optics lab, IIT Madras. And if you want to have further details, you can go to this reference. And there is always a discussion in academic circles whether to label a method as speckle interferometry or holography. This debate is on. They have called it as TV holography here, 3D surface profile characterization and so on. So, this debate is always on. And in speckle interferometry also you can get the displacement vector. And I had mentioned earlier, when you get a displacement vector, interpretation becomes little more complex, and you need to have methods. And if you go to this literature, they will talk of something like sensitivity vector and how to extract data. These are all mathematical details. We are not getting into those mathematical details at this stage. Our focus is mainly to appreciate the principles involved in various techniques, and also look at broadly for which class of problems these techniques are applicable, and also limitations, broadly speaking what way these techniques look and how these can be compared, some kind of an information which will aid you to arrive at a appropriate technique for the given application. So, what you find here is mostly you will get out of plane displacement measurements, but you can get the displacement vector by choosing appropriately the illumination viewing angles and also constraining the object motion. This is common to both hologram interferometry and speckle interferometry. If you want to get U and V displacement, and you have to choose the illumination, viewing angles, and also constraining the object motion. All these have to be used for finding out specific components of displacements. On the other hand, Moire, by choosing the grating, your interpretation becomes simple. Here it is involved because you collect more information, and so you have to be systematic in filtering out what is it that you need. And another popular version of speckle interferometry is shearography, and this is a very useful technique for non-destructive testing. In fact, for honeycomb panels, this is the very popular technique, with composites becoming very important structural materials. There again you have problem of delamination, and techniques like this go a long way in identifying and this shows the sharing element. We will have a closer look of it. So, what I have is I have a beam splitter, one ray goes straight and hits this mirror and comes back, the other ray goes there and gets sheared, and on the image plane you have for one incident ray two rays are seen. Same thing you can watch it for the second ray. So, I get one ray from the mirror 2 and I get another ray from mirror 1. You make a sketch of it, I will do the repeat the animation again for you to understand how you perceive this, and because of the shearing action you essentially measure the slope. You measure the slope essentially. So, you have the ray goes and hits this mirror, this is kept perpendicular and the mirror 1 is slightly tilted. So, beam splitter sends one ray to this mirror and sends other component to this, and whatever comes from this, because of the tilt it gets shifted, and this is called, it is also said it is sheared to this point. So, for each incident ray you will have two rays impinging on the image plane, and we will just have a look at the animation again. And this is what you see here. I have the ray goes straight and hits this mirror, another component goes to mirror 1 and this gets sheared. And in shearography the vibration isolation requirements are less stringent, that is why it has become a very popular technique in industry, and many manufacturers are giving out shearographic equipment. It is used routinely for non-destructive testing of several composite panels, honeycomb panels and so on. And when you do this, what do you get? You get essentially slope fringes, and we have also noted that these are butterfly fringes because of the shape, because on the shop floor they would like to classify this as butterfly fringes for easy identification. In fact, it is dou w by dou x contours. So, what we find here is, by introducing a lateral shearing element in the optical path, one can get fringes corresponding to the slope of out of plane displacements, that is what you get here. And this, there is nothing like one is a reference for the other is a reference for this, there is nothing like a single reference beam for fringe formation, and hence robust for an industrial scenario. So, what you find here is shearography is a robust technique compared to speckle interferometry or hologram interferometry. If you put a shearing element, it makes your life lot more simpler, and you get only slope information. You get only a slope information, you do not get out of plane displacement. So, that is the difference. It makes your experiment simpler, at the same time gives you a different type of information. So, in this class we continue our discussion on speckle interferometry. We saw what is shearography,